we have to then talk about briefly the equation of state with respect to gas condensates. What's special about gas condensate systems in developing an equation of state? So if you haven't seen it, I'd recommend that you see here. If you go into the basically our home page and look under company and news, I already mentioned that this what we call monthly article about blockage. I'd like you to look at that before tomorrow. It's just a short, 7-8 page thing. But this one is the last month. This is Marcus Nielsen wrote this, and this is a very nice introduction to what is an equation of state. And what's it used for? What do they look like? How do you calculate? And then it talks about the different names: the Redlich-Kwong, Swalver, Redlich-Kwong, Pang-Robinson. And then the most important thing is getting to the two tables representing the equation of state. Again, it's two tables. It's the set of component properties, and it's the so-called binary interaction parameters. These are the two tables of an equation of state. It also defines how what we're calling the components in the mixture, so the list of component names, together with the properties of each component and the so-called binary interaction parameter. So this is a very nice short summary of the equation of state. And we can look at this equation of state. I don't know if it's I'm not sure where the okay, maybe it doesn't reproduce the. I have to go to the input file. Yeah. Okay, so you get so here's this for the for this COOF paper. So the table will contain the component names, molecular weight, critical temperature, critical pressure, the volume shift, and the acentric factor. Those are the main properties that must be specified. The paracores, they're for calculating the interfacial tension of gas and oil, between gas and oil. And the critical Z factor is, in this case, used in the viscosity correlation called Lorenz, Bray, and Clark. But the equation of state properties themselves that are required are these three: the TC, PC, and molecular weight, together with the acentric factor and the volume shift. Those are the component properties. And then comes the binary interaction parameter table. So between each component pair, there's a number, typically 0. But this is the Redlich-Kwong equation of state, I think, the Swalver-Redlich-Kwong. So often the hydrocarbon BIPs are close to 0 or assume 0. And I think that's the case for this EOS. It looks like there's one BIP between, I think, methane and C30 plus. Let's look at the table from the paper. A little better format. Okay, so these are the properties: molecular weight, TC, PC, acentric factor, volume shift. And then these are the BIPs. There's always non-zero BIPs for the non-hydrocarbons, H2S, and then there's one hydrocarbon BIP between methane and the C30 plus, magnitude of 0.06887. So those are the two tables for the equation of state. And then you need a composition, of course, to use the equation of state. So compositions are given for the K1, K4 formation, the K2, K3 formation, and then some kind of a approximate Gawar composition here. Basically, these are identical except for methane and H2S. So there's more H2S in this formation. Okay. Any questions about just the general about equations of state? So there's two tables. Well, so it's either the SRK or the Peng-Robinson. You have to specify which one it is. And there's the original, this is the, I think it's called Peng-Robinson 79 and Peng-Robinson 77. 76. This is the original, which almost no one uses. Not used much. And this is usually the default, the modified. And I think is default in most programs. So the table 1 are component properties. So it's the name of the component, nitrogen, etc. Molecular weight, TC, PC, acentric factor, and the so-called volume shift factor is either dimensionless, S, or with dimensions, C. Those are the required properties you need for the equation of state. And then table 2 are the so-called binary interaction parameters. And the symbol for them are Kij. So you've got no interactions between components and themselves. It's a symmetric matrix. So it has symmetry. Methane C30 plus is the same as C30 plus methane. And the magnitude is typically plus minus 0.1, maybe to 0.2. And it's typically maybe minus 0.1 to plus 0.2. You always have non-hydrocarbon non-zero BIPs. These are library, and they're all close to 0.1, 0.07, 0.13 CO2. So for that would be CO2, H2S, and nitrogen. Yeah, I think that's the main things you need to know about it. Now, so what I wanted to mention were what's special about gas condensate systems and equation of state. Okay. So what's special here? We mentioned yesterday is probably the most important thing is in the tuning of an equation of state. You want to get the composition of the CVD removed gas compositions of the C6 plus, C7 plus, whatever you wanted to use. It doesn't really matter. You know, some kind of N plus. So that would be C6 plus or C7 plus, C5 plus, whatever you want. Basically, as a function of pressure, the match is very important because that's really related to the little rs. Okay. You'll typically get the dew point, but you know you have this uncertainty of anywhere from 10 to as much as 500 psi because of this liquid dropout tail. We already discussed when it's important to get the dew point right and when it's not. The Z factor should be, you know, plus minus 1 to 3%. And the C7 plus distribution, be it lab GC or extrapolated with some kind of a distribution model, it has big effect on saturation pressure, dew point, and potentially liquid dropout, you know, small values of the liquid dropout relative oil volume. But also it has a big impact on the incipient oil properties. And we often don't know anything about the equilibrium oil properties in a gas condensate. We don't usually measure the oil composition. So as an example, this will have a big effect on this GOC prediction if you're doing a compositional gradient. So the heavy ends distribution can have a big effect on the EOS tuning of the dew point when it's important, and then the use of the equation of state for predicting, for example, oil below deeper in the reservoir. And the last thing is that oil viscosities are not usually measured. Usually measured because the amount of the reservoir liquid condensing is small. It's not easy to get the viscosity. So so what we recommend is that you take, if you have separator samples, to use the separator oil in a PVT cell by itself, but you bring it to reservoir temperature and you bring it to pressures ranging from about 500 to 3000 psi. This might be saturation pressure or separator pressure, the low end here, from separator pressure, for example, around there. So in this range here, to measure single phase oil viscosities of the separator oil by itself. And then use this data to tune the viscosity model. I think those are the most important things in relation to developing the EOS for gas condensates. Certainly this one is always the case. But I think all of these are standard. I mean, if you do these things right, you do these things diligently, whatever package you're using, it should be okay. Now, most packages won't let you match the the C6 plus of the equilibrium CVD gas. So that there you have a bit of a problem. So even if you can't tune it with the regression, you still can try to make it match by hook or by crook. Okay, so I think we'll take a break there.
We have Marcus just mentioned to remind about the webinar on EOS tuning, since it's very relevant to this.
Oh, okay, yeah. Yeah, the webinar is
it's on the 15th of July.
July 15th webinar. And I'm sure, hopefully somebody will remind me, I'm sure we'll have, that'll make some kind of comments about EOS tuning specific to gas condensates. It'll be a kind of a summary of this, hopefully.
Yeah.
Remember to do that.
It's free to sign up.
Yeah, so it's free to sign up. And you can go to LinkedIn, to our, just find the Whitson on LinkedIn, the company, not Curtis, and you can sign up for the webinar. It's the registration is still open.
Company. Okay.